Vector databases give AI apps long-term memory and semantic search. But in 2026, low search latency for edge and on-prem deployments is driving a new wave of AI use cases that simply aren't suitable for cloud-hosted solutions. So in this video, I'll explain what vector databases are, how they work, and why performance and efficiency matter more than ever. Vector databases exist because traditional databases and search engines can only match on exact keywords, not similarity and relevance. For example, if a customer types "my payment didn't go through" into a support chat window, they need results about billing failures, declined transactions, or card processing errors, none of which match their keywords. But a vector database can retrieve them based on the semantic similarity to their query. So instead of the structured text stored within tables or documents, a vector database can store any type of data encoded as a vector. These vectors are produced by embedding models, which are models trained to convert input data like text, images, or audio into multi-dimensional lists of numbers that place concepts close together when plotted in vector space. Choosing the right embedding model is a trade-off between speed, cost, and accuracy, where the model's training data, output dimensions, and architecture all affect both performance and semantic quality. We'll dive deeper into embedding models in the second video of this series. Vector search works by first encoding the user's full query into a vector, then comparing it against stored vectors using a similarity or distance function to find the closest matches. To make things more concrete, let's look at some code that shows how vector search works at the most basic level. Here I'm using Google's embedding Gemma model, a great performing model that's easy to run locally. First, we generate vectors for each document, which would normally be persisted to the database. The search function requests the query, converts it to a vector, then computes the cosine similarity score between the query and each vector. So let's give the script a run. Loading the model and generating the vectors does take a bit of time, but this only happens once. So I'll search for drums, and as you'd expect, it ranks closest to cymbals. But when I search for strings, it ranks closer to guitar. This is a simple example, I know, but the point is to show you the order of operations and to demystify how ranking actually works. Now let's move on to how search and indexing work at scale. Vector search isn't really about exact answers. It's about managing the trade-offs between speed, recall, and resource usage for fetching the most relevant content as fast as possible. Comparing a query against every vector in a database would be great, but this doesn't scale, so indexing is required to keep latency low for real-world datasets. Most systems use approximate nearest neighbor, or ANN indexes, that organize vectors into similar regions. When a query comes in, the index navigates towards regions likely to contain relevant results. The goal is to scan only a subset of vectors, trading a small and acceptable loss in recall for significant gains in speed and efficiency. I'll be covering specific indexing strategies later in this series. Choosing the right vector database depends on where and how you plan to run it, as a cloud-hosted service has very different trade-offs than a system designed for on-prem or edge deployments. Cloud environments benefit from elastic infrastructure, but with the downside of usage-based pricing. On-prem and edge environments offer more predictable costs and lower latency due to data locality, but CPU and memory are more fixed and constrained. That's why efficiency is so crucial. The indexing strategy, query computation overhead, and memory layout all affect search latency, and two databases using identical indexing algorithms can still perform very differently. Comparing vector database performance between vendors can be a bit difficult, so a good starting point is using tools like ANN benchmarks and VectorDB Bench, which track metrics such as query latency, recall, and resource usage across a wide range of vendors. So now you know what vector databases are, how semantic search works, and why performance matters, especially at the edge or on-prem. Thanks for watching, and I hope to see you in the next video.